Welcome to our third installment on the section on data handling. You'll remember that we were looking at measures of central tendency as well as spread in our first session, and then we spent time looking at how to represent data in our second session. Today we're going to focus on looking at further representations of data as well as learning how to read graphs and charts to gain statistical information. So to start off with today, we need a set of data. Let's have a look at what we can use here. A survey was done asking families how many children they have in their family. And the results were as follows. 35 families had 0 children. 56 had 1 child. 79 families had 2 children. 51 families had 3 children. 20 families had 4 children. And 11 families had 5, and lastly, 1 family had 6 children. There are several ways of representing this data. You'll remember that we used the bar chart, the histogram, and the pie chart in our previous sessions. The bar chart would be quite adequate to represent this data. On our x-axis, we put the number of children from 0 right up to 6, and then the column height would be the number of families in each section. If we were considering, for example, that these were all the families in one school, then the families as a total would represent 100% of the data. In this case, a pie chart would also be a suitable way to represent the data. We'd divide the pie up into sections for each child, 0 again to 6. And the number of families would be the percentage of families that have that number of children in each section. But there are other ways of representing data, and some of them are a little more useful in determining information from that data. So let's look at some new ways that we can represent this same data. One of the ways to represent this data is by using a frequency table. We're also going to be interested in calculating the cumulative frequency. Now, the word cumulative simply means to add together. So when you see that you need to prepare a cumulative frequency table, we're going to have to add some of the data together. The word frequency tells us how often a data sample appears. A cumulative frequency table is another method of organizing data. So let's take our previous example with the number of children and the number of families that have these children. Remember, we had 0 children, there were 35 families. 1 child in the family, there were 56 families like that. And so on down to the bottom where we had 6 children and only 1 family had that. To calculate the cumulative frequency, frequency meaning the number of times that data sample appears. In our first case, 0 appeared 35 times. That's the frequency. So to start with, we've got a 35 over here. Now we have, for 1 child, there are 56 families. In this table, we want to add that together. We're going to keep a running total of the number of families. So the number that will go in here is 35 plus the 56. That takes us to 91. Going further, we now have to add in 79 families. So 91 plus 79 takes us to 170. And so we go on right down the table, adding up carefully. 221, 241, 52, and lastly, one more family, 253. So this column over here is simply a total of all the families as they keep having more children from 0 up to 6. Now, when you're filling in tables like this in an exam, it's very easy again to make a mistake. I recommend that you fill the table in and check yourself by doing the adding twice. It's very easy to go wrong, and it is worthwhile to actually take the values and do them twice. You will save a lot of time by having not to correct any mistakes later on. On the far right, you can see that we have another column, and this one says cumulative percentage. This is something that we'll be very interested in drawing a new graph later on. How do we calculate the percentage? Well, we've got the total number of families already, 253 families. That's 100% of the data that we've been given. So to work out the percentage, we're going to go 35, because that's how many families we had for 0 children, divided by 253. Let me write that over here. 35 divided by 253. I'm going to use my calculator to get that percentage. 35 divided by 253 equals, and of course we'll multiply by 100 over 1. That's a percentage of 13.8%. So let's fill it in over here. 13.8. For the next family, it was 91 was the total. It would be 91 divided by 253. That would give me the next cumulative percentage. Of course, if I only wanted the percentage of the families that had 1 children, I'd have to use another number. It would be this one, 56. So if I said 56 divided by 253, and let's do the calculation, that would equal 56 divided by 253 times 100. That would be 22% of the families that we have in total, or 22.1%. If I added 22.1% to the 13.8%, I'm getting a cumulative percentage frequency. That would come to a total of 35.9%. Sorry, let's just erase that. 35.9%. Well, let's check if 91 divided by 253 also gives us 35.9%. I'm going to go straight to the calculator. 91 divided by 253 and multiply that by 100. And we get 35.96. All right, if we rounded that up, we'd have got 36%, wouldn't we? But for the purposes of our calculation, this is acceptable at this stage. 35.9% is what 91 represents, 91 families. So this is a nice way of checking. You can either take the cumulative numbers and keep dividing them by 253 to get a percentage. And then you can say, let's check what adding the single family for each category would give us. For example, in the next one, I know that 79 families out of 253, let's see what that would give us as a percentage. And that would be 31.2%. So this value on its own is 31.2. But what is 170? Which is our cumulative value again. That one is 67.2%. And again, a way to check, if I add 31.2 to 35.9, will I get 67.2? Well, 31 and 35 is already 66, and 9 and 2, 9 and 2 would actually be 1. Again, for the purposes of the calculation, it is acceptable or an acceptable margin of error at this stage. Let's keep adding. 221 Now we're at 87.3%. 241. 95.3%. We'll round up this time. 252. And that's 99.6%. Let's just round it to 99.6 there. The last one is going to add the last 0.4%, and so our total comes to 100%. Now, sometimes when you're doing this calculation and you use the original values and keep adding them up, you might get to a figure in the final block that is 99, something percent, say 3%. It's not quite 100%. And that's okay, as long as it's not something like 94 or 93%, or even maybe 97 could be a little bit too far away from 100. If you get to the 99, something, you pretty much can guarantee that you've done the calculation correctly. The reason for the slight variation is simply that we've continuously rounded off our values. We haven't used all the digits that the calculator gave us, and so that is why we don't quite get to 100%. Obviously, we could also possibly go slightly over 100% to maybe 101% or 100.4%. That would also still be an acceptable margin of error for this type of calculation. Now, once we have the cumulative frequency and the cumulative frequency percentage, we can use this data to plot a graph for ourselves. You can see over here, I've set up an axis system. On the x side, I've got the number of children per family. And we had 0, 1, 2, 3, 4, 5, and 6. This was the range of the children in each of the families that we had. On the left-hand side, you can see that my y-axis is going to go up in percentages. So I'm going to mark off just 20%, 40, 60, 80, and 100. We're now going to use the data from the cumulative percentage frequency to plot a curve. Let's go back quickly and get our values. We started off, 0 children was at 13.8%. So for 0, I need to be somewhere around here. I'm going to make a plot point over there. When we got to 1, we saw that that was 35.9% as a cumulative frequency. And remember, we're plotting the cumulative frequency now. So that becomes 35.9. That's just before the 40, round about there. Once we were at 2 children, we were at 67.2. Let's make a mark over there. For 3 children, we got to 87.3. So that's round about there. For 4 children, we were now at 95.3, and then we went to 99, so we're going to do both of those. 4 children, 95, 5 children, 99, and lastly, 6 children, 100%. We can join the dots of our curve. And we get something that looks as follows. In statistics, this is sometimes known as an SCurve or an ogive. You may have seen that word in a textbook somewhere. This type of plot, the SCurve, is also known as an ogive, as you can see over here. It is useful for reading information regarding an amount below a certain value or a percentage. If you look back at our table, we can use this chart and ask a question of it. I could say, for example, how many families fall below the 60% mark in terms of the number of children that they have? Well, here we have the 60% mark. Going down my curve, you can see it falls somewhere between 1 and 2 children. Now, of course, we don't want to have 1.5 children again, do we? So we could just simply say that 60% of the families in this school or in this sample that we've chosen have a family that has either 1 or 2 children or falls between 1 or 2 children. We could also say that they have an average amongst them, 60% of the families, of perhaps 1.7 children. That's the average or the mean, if you remember from our first presentation. The SCurve is a very useful chart indeed, and we'll be using it a lot in further examples. Another way of representing data is to use a stem and leaf diagram. Let's have a look at how that works. A stem and leaf diagram is helpful in organizing larger amounts of data that relies on using a common place value as a stem and then using the next place value as the leaf. I'll explain that in a minute with an example. Let's take an example here. Given that students scored the following results in their cycle test, and there's the list of results, we can arrange this data as follows. Now look what we've done. We've used the tens unit as a stem and the ones or digit units as an leaf. So in other words, taking the number 50, which was one of the results that we had, the 5 is a stem and the 0 is a leaf. Now in this example, there are several 5 values or values in their 50s. Let's mark them quickly. There's one, there's another, a third, and we have a fourth over here. Notice how we arranged this data on the stem and leaf diagram or table. There's 5, and we've got 0, 2, 5, and 8 as leaves. 0, 2, 5, and 8. All 4 the cycle test marks that were in their 50s are represented in this chart. We've done that for all the values that we were given. So if you were reading the values off for the cycle test, you would say 38 was a value, 40 was one of the sample values we got for this test, 45, 47, 50, 52, 55, 58, 63, 65, 68, etc., etc. This diagram is useful for categorizing the data into intervals. In this case, I might be more interested, for example, in knowing how many students fell in the bracket of 60 to 69%. Then I would have a look at this section of my chart. And because I've got 1, 2, 3, 4, 5 leaves, that means I've got 5 readings or 5 data samples in that bracket. So I could answer the question that there were 5 students who fell into the bracket of 60 to 69%. And the stem and leaf plot gives us a very nice indication of how to categorize data. I'm sure you'll agree that this is a much better way of representing data when we are looking for categories. Another example of how we can categorize data or represent data is with a box and whisker diagram. Now, this is not the kind of box where you keep your kitten in. That's where the whiskers would come in. A box and whisker diagram is useful for listing medians and quartiles, as well as determining the range and giving information on spread. You'll remember from our first presentation, we dealt with medians and modes. We also dealt with range and things such as the interquartile range. Those were the measures of central tendency and the measures of spread. Let's have a look at what a box and whisker diagram looks like. You'll see that we have a box over here, or two actually, with a line running down the middle, and on either side we have two lines that extend. Those are the whiskers of the diagram. With these, there'll always be a series of numbers. Sometimes the box and whisker diagram is also known as the 5-number summary, because there are always 5 numbers associated with a box and whisker diagram. Here they are, 1, 2, 3, 4, and 5. The number that is situated by the line or the division in the two boxes is simply our median value. Remember, the median is that value that appears right in the center of the data. It literally tells us that 50% of the data was above that value and 50% was below that value. I'm sure you can guess at what the numbers on either side are. The numbers 10 and 20 that we have here are our two quartiles. Quartile 1, or the first quartile, on the left-hand side, and quartile 3, or the third quartile, on the right-hand side. So 10 is the first quartile, 20 is the third quartile. So we can get the interquartile range if we wanted from these two values. That would simply mean taking the 20 and subtracting the 10. So on either side of the median, we have the two quartiles on the edge of the boxes. And then we have a further two numbers situated right on the ends of the whiskers. These two values represent the extremes of the sample, the lowest and the highest value that we got from the sample. And so these two values will give us the range of the data that we have been given. In this case, the 24 minus the 5 gives us a range of 21. So the 5 numbers that we get given in a box and whisker diagram are the extreme values, the first and the third quartile, and then the median, which is also sometimes known as the second quartile. What the box and whisker diagram also does for us is it gives us an indication of how the data in the sample is spread. Notice, for example, here, that this section is narrower than from the median to the third quartile. The range of data from the first quartile to the median is only 4, whereas from here, from the median to the third quartile, it is 6. That's why the box is wider here than it is over here. Similarly, we can indicate how far away the values of the range are away from the box, or from the first and third quartile. In this case, they were both pretty similar in distance. There's a distance of 5 between the 5 and the 10, and there's a distance of 4 between the 20 and 24. Now, why a box and whisker diagram is useful is because we can determine from it whether a number on the extreme end of our data sample is an outlier or not. Remember, when we were doing this earlier, we spoke about outliers. Those are values that appear in our sample, but because they are so far removed from the median values of the sample, they actually can be ignored. Now, it's not that we just ignore them because they're far away. We can actually check whether we should ignore them or if they are actually part of the sample by using a formula. You can see here, we've already used this to get our Q1 and Q3 values and our interquartile range. Let's put that in quickly. 10, 14, and 20 were the values we were interested in, and Q1 was 10, and Q3 was 20. Interquartile range was 10. Remember, that is 20 minus the 10. Now, Using this formula, and again, you don't have to go and learn this formula. If they want you to use this formula at all, they will give it to you. I have at times seen this in an exam paper, but then it was given. So we know that Q1 was 10. We're going to subtract 1,5 times the IQR being interquartile range, and that again was 10. So 1,5 times 10 is 15. That means we have 10 minus 15, which equals -5. Don't worry that the number comes out as a negative. That can possibly happen at times. On the other side, we're going to do it for the Q3 value, and to find out if the number is an outlier, we're going to use the Q3 value, which was 20. We're going to add 1,5 times the IQR, which again was 10. That gives us an answer of 20 plus 15, which equals 35. Now, these two values that we've calculated give us the extreme of the range before we should start considering that the number is an outlier. In other words, if I have a value that is -5 or lower, or I have a value at the other side of my sample that is 35 or greater, I would be entitled to call that value an outlier, and I would be able to discard it in my sample. Going back to the box and whisker diagram, we can see that 24 does not fall beyond the range of 35, nor does the 5 fall beyond the range of -5. So both of these values in my range are legitimate numbers in my sample, and I would not be able to discard them for fear of actually changing the data in my sample. Just because a number is high does not necessarily mean it must be thrown away. It is useful to check using those formulas whether a number should be discarded or not. Moving on, we're going to look at another or a fourth representation of data. And that is in a chart known as a percentile chart. Now, percentile charts are very much like ogives. In fact, they are ogives. They're just ogives with many different lines on them. A chart with many ogive type lines indicating the percentage cutoffs for a sample. Let's have a look at a real-life example of a chart. Now, don't be too afraid by the amount of data that is represented on these charts. There is a lot of information given here, and we're going to need to use this information to answer a number of questions. This chart says that we are dealing with the body mass index for age percentiles for boys aged 2 to 20 years. On the left-hand side, as well as on the right-hand side, in the Y direction, they've given us the data known as BMI. BMI simply stands for body mass index. They've also told us at the bottom here, if you can see that, the kilograms per meter squared. That's simply the units that body mass index are measured in. Let me write this over here so you can see it in a little bit more detail. BMI is actually a calculation that measures the weight over the height of a person squared, and the height needs to be given in meters. That's where they got these units from, the kilogram per meter squared. So let's do a quick example just to show you. Say now you weighed 65 kilograms and you measured 1,6 meters in height. To calculate your body mass index, we'd do the following. We'd say 65 kilos divided by 1,6, that's your height in meters, and we'd need to square that. Going to the calculator, 65 divided by 1.6, and we want to square that to the power 2, the answer comes out at 25,3. If we rounded it up, it's actually going to be 25,4. So let's do that, 25,4. You would then be able to go and have a look at where you fall in relation to a whole lot of other people for which this sample was taken. This is a standardized example or a standardized set of data. So what we're getting from here is that boys aged 2 to 20, if I fall within that age range, I can actually work out how I relate to the rest of a population where this data was taken from. My data was 25,4 for my BMI. Having a look on the left-hand or the right-hand side, it doesn't really matter, 25,4 is round about here. Now, I'd also need to know my age. Well, let's say that the person that we used here was 15 years of age. That means over here. So we've got a BMI of 25,4. We've got an age of 15. Let's have a look at where those 2 points intersect on my chart. That's round about over here. Sorry, there we go. Now, having a look at this, if you look at these lines, I'm falling between the line that says 90th and 95th. This curve runs all the way from the left up here, and so do many of the others. My dot falls between 95 and 90. What this chart is then telling me is that for me weighing 65 kilos, being 1,6 meters in height, and being age 15, I would fall between 90 and 95% of the population. I'd be in the 90 to 95th percentile. The 50th percentile, which is this dark line that runs through the middle, is the median. So a quick question. Do I fall above or below the median? Well, it's clear from the chart. I'm above the median. That means I'm above average in relation to the population. If I looked at the median BMI for a 15-year-old, that would be the point over here. And reading across, that means I would fall within a BMI of 20. So my BMI, my body mass index of 25, is above average for a 15-year-old. Now you might say, why have they gone from 5%, for example, to 95? Remember the work we did on standard deviation? We said that 95% of a sample usually falls within 2 standard deviations of a sample. On a BMI chart such as this one, what we're actually saying is that 90%, because we're going from 5% to 95%, leaving a 5% on either side, is the range of normality. In other words, looking down here again at our 15-year-old, starting at the 5th percentile, which is literally at about 16,5 BMI, let's write that value down, and going right up for the 15-year-old to the 95th percentile, that's a BMI of around about 27. What we can say about that range, 16,5 to 27, is that it is the normal range. Or it is the range that falls within 2 standard deviations. Let's erase that and write it on the next line. Two standard deviations. So for a 15-year-old to be considered normal, and I know there are not many of those around, just joking, 16,5 to 27 is their normal range. Anybody with a BMI above 27 would be considered obese, and anybody below 16,5 would be considered too thin or anorexic for their age. You see, if you go to the doctor now and you go and do some tests and they take your weight and they measure your height and they calculate your BMI, they're going to be able to tell you, using a chart just like this one, whether you are actually in the right range of values for your age group. If you look at this graph, we can see that a 50 percentile for our 15-year-old was round about, we said 20. But take that value of BMI of 20 and let's go down to someone who is 4 years of age. Notice what that means. A 4-year-old with a body mass index of 20 would not be considered falling within the normal range. They would be way outside and would be considered obese for their age. Do you see that it's not to do with the actual BMI? It's to do with the age as related to the BMI on this chart. We need to consider where those values fall in relation to the line. Let's go and take a look at one more example. I've actually got some questions here related to this. It says that the following children indicates the weights of the school children in the grade 4 classes. So what we've got here is a range of weights, and we've got a number of children on each weight. So that's the frequency. What would I need to do for this? Well, I'm going to plot a cumulative frequency chart. And using this chart, I'll plot an ogive and then answer the questions that follow. So, for 30 to 32, that category had 5 children. Again, our cumulative frequency is 5. Our cumulative percentage frequency would be 5 out of our total. We'll get to our total in a moment. Adding up here, we've got 7 in this category, so the cumulative frequency must be 5 plus the 7, which is 12. 12 plus 11 takes us to 23. 23 plus 17 takes us to 40. 40 plus 13, we've got 53. 53 plus 9, 62. And lastly, 62 plus 3 gives us 65. There we have our cumulative frequency totals. To calculate the percentage, we're going to have to say 5 out of the total, which is 65. Again, we'll need our calculator for this. 5 divided by 65 equals, multiply by 100 to get percentage. And we've got 7,6. Let's make it 7,7%. Now, for 12 divided by 65, and that gives us 18,5%. 23 divided by 65, sorry. That will be 35,4%. 40 divided by 65, 61,5. 53. And we're at 81,5%. 62. And that gives us 95,4. And of course, if we divide 65 by 65, we're going to get 100%. So now we have our cumulative frequency chart. This can be used to plot an ogive. There's our axes. We're going to want categories on them from 32 up to 44. 32. Let's just move this down a little bit more. 34, 36, 38, 40, 42, and 44. Remember, we had 5 children in the first one, but what we're interested in is the percentage frequency. So on the left-hand axis, we're going to go with percentages again. 20, 40, 60, 80, and 100. From 32 to 34 was 7.7%, round about there. I'm going to use the center of the data to plot the value. 18.5% is the cumulative frequency from 34 to 36, so that's just under the 20. 35.4 for the next category. 35.4, round about there. 61.5. Sorry, we're actually 1 point below. We should have done this here. Let's move them quickly. It won't take me long. So we actually want to start about here with our 7.7%. So let's plot that value there. And the 18.5 was there. The 35.4 is the next value. 35.4. Between 36 and 38, 61.5 is our cumulative frequency. That's round about there. Then we've got 81.5 when we get to 38 to 40. 81.5. 95 for the next one, and of course 100 for the last. So 95 round about there, and 100 for the last. Again, joining our plots, we get something that looks like that, a similar S-type curve or ogive. So now we have our cumulative frequency. Let's go and see what questions we have from this. I've asked the question, what percentage of children are below 38 kilograms? Well, going to look at my plot that I've drawn, 38 kilograms is here. If I take a line up and I go across, I'm going to say about 90%. Again, my accuracy of my diagram hasn't been that great here when I'm drawing, but you will be given graph paper to do this, to make sure that you can do an accurate representation. Reading off my chart simply, to answer that question, I'm going to say 90% of the children fell below 38 kilograms. Another question that I might be interested in, and they love asking this one, is what would the median weight of this group of children be? Well, I've got to know what median means again, and that means that it is 50%. So on my chart, I'm going to find 50% on the y-axis. I'm going to draw a line across and see where or which weight that will give me on my x-axis. You can see that it falls somewhere between 34 and 36. So let's make that 35 kilograms. So to answer this question, what would the median weight of this group of children be? The answer is 35 kilograms. Notice, I haven't used the table for this data. I've actually used the plot that I made from the table. Another question that they like asking is what would the range of weights be that cover 95% of the sample? Remember, for 95%, we're talking about the 2 standard deviations. So really what I'm asking here is what is the range within which 95% of the sample would fall, or for what would be the range for 2 standard deviations away from my mean, which was that 35 kilograms. Well, for 95%, I would have to be somewhere over here, because I'm only going to have 2.5% at the bottom, and I'm going to have 97.5% at the top. So 2.5% over here is the reading, 2.5. Here it is 97.5. I would want to find what weights, let's join that line nicely together. I would find what weight falls at 97.5% and what weight falls at 2.5%, literally right down here. I'd say this is about 30 kilograms. And here for the 97, we're looking at maybe, say, 39.5. So what we can say for this one is that the range, let's just extend our page, the range goes from 30 kilograms to 39.5 kilograms. That range would cover 95% of this sample. Anybody falling outside of those two values, less than 30 or above 39.5, would be considered to be falling into the abnormal range of data, or they would be considered to be outliers in this region. They would fall into the 2.5% or 5% on 2.5% on either side and 5% in total of the population of that data. In other words, there would be less than 5% that would have either a weight less than 30 or above 39.5 in the sample that we've done. Shall we take a look at another example? Here's one on drawing a stem and leaf plot. Let's see if we can do that as well today. We get given a series of data for a cricket score. These were collected for a player over 20 matches. In other words, these are the 20 scores that he scored over 20 playings. Well, to draw up or set up a stem and leaf plot, I'm going to need a stem. And my tens digit is great to use for a stem here. I'm sure some of you have already picked up that we've got some values that go up into the hundreds. That's okay. In the tens digit, we're simply going to make that a 10 for our stem. So let's draw up a stem and leaf. We'll divide that up. Right. What is the lowest stem that we have? Well, we can see we have a score of 0. So the stem has to be 0, and the leaf also has to be 0 in this case. The next one, we've got some that are in the single digits. So the stem is still 0, but we've got a 7. No tens units, but 1 7. Are there any others that fall into the single digits? No, we've covered all of those. So let's cross them off so we don't get confused with them later on. The next values up, we've got some digits where there are tens, so a stem of 1. And I can see I've got 11 and 11, so there's a 1 and a 1 here. Cross them off. There's also a 16, that means I've got a 6. We'll cross that off. Moving on, we've got a 2. There's a 23. We've got a 29. We've also got a 28. And we've got a 25. That takes care of all the 2s. Now we're going to go to 3. There's a 37 and a 32. Now, some of you might have noticed that I've already missed a value out. Can you see where it is? Yes, it's this value, the 19. But it's easy just to go and add it into our table. Remember, that's a stem 1 and a 9. Do you see why the stem and leaf plot is more useful in organizing the data? Especially when I'm trying to get it in order. I can make mistakes and not miss out on anything and go back and fix those mistakes. Whereas if I was just listing the data from left to right, I'd have to rewrite all of the data, which is not very helpful. Carrying on with our plot, we've got stem 4. Any data here? There's a 40 and a 49. I've also missed that 29 over there, so I'm going to fill it in for myself over here. Sorry, did I cover that one already? I don't think I crossed it off, that's all. Okay, we can erase that one. We have got it on our chart. Four was 40 and 49. Let's cross these off. We've still got a 53, a 61, 73, 94, and the 200 scores. So for 5, we've got 53. For 6, we've got 61. And we need 73, 94, 7, and 3. We don't have anything on the 8, so let's just put it there, but we won't put any data for it. 9 had a 4, and then 10 had a 2, because we had 102. And lastly, we've got 108. Another good way of checking now is to see that we've covered all the data samples by counting up how many leaves we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 leaves. 18, 19, 20. Well, 20 was the number of scores that we had. So we've now got all our data represented on this chart. On our stem and leaf plot, we can easily calculate things like the median, as we did before with ordered data. Let me quickly show you how to do that so that you can use this method in your exams. This is an ordered set of data. So there is a middle value for this data. Starting at the bottom, I would cross off 1 and cross off 1 from the top. And so I would keep going until I get to my center value. There's 1 there. Now we're over here. Remember to go backwards from the bottom, but forwards from the top. 6 is the next one to go. 1 is the next one to go here. 9 and 3. 3 and 9. 5 and 0. 8 and 7. And you can see we are left with 2 values in the middle here. This is the value 29, and this is the value 32. So those are the 2 median values. To find our median, I take those 2 values and add them together. 29 plus 32 and divide by 2. The answer simply comes out at 30,5. So again, the stem leaf plot is very useful in terms of getting our data such as median, and we can do the same for quartiles, just like we did when we organized our data from lowest to highest. If I asked you for the range, for example, here we can see that our lowest value was a 0, the 0 stem and the 0 leaf. What was the highest value? Well, the stem was 10 and the leaf was 8, so that came out as a value of 108. So our range equals 0 to 108 for this example. Let's take another look at a new example, and we're going to look at how to find outliers. Again, this is going to relate to the box and whisker diagram. Here I get given a sample, and it asks the question, find out if the following sample has any outliers. On the surface of things, I might think that this number 49 is an outlier. It does look like it's quite far away from the rest of the sample. But I would need to check this and make sure that this is the case. So to start with, we need to find the median. The middle value, crossing off on either side, leaves me with 25. 25 sits in the center of this sample. To find quartile 1, I'm going to find the value that's in the middle of the bottom half of the data. In this case, 23 is in the middle. Here, 33 is in the middle. So quartile 1 is 23, and quartile 3 is 33. The interquartile range, or IQR, is simply those two values subtracted from each other. That gives me an answer of 10. What are the extreme values for our sample? Our lowest was 21. Our highest was 49. Let's go back and use that formula to see whether we do have an outlier in this sample or not. Remember, we needed the Q1 value, and we're going to subtract from the Q1 value 1,5 times the interquartile range, which in this case was 10. So that'll be 1,5 times 10. Q1 we said was 23. So 23 minus 15 equals 8. That means that for a value to be an outlier, it would have to be 8 or below. In my case, my low value was 21. So it is well within the range of being in the sample and does not need to be discarded. On the other side, checking if the number 49 is an outlier, we'll need the Q3 value. And here we'll have to add 1,5 times the interquartile range, which again was 10. The Q3 was 33, and the 1,5 times 10 is 15. So 33 plus 15 gives me an answer of 48. Well, the extreme value that I had was 49. And so it is bigger than the value 48. So I can legitimately discard this value 49 and say that it is an outlier, a number that does not really form part of my sample. Going back to my sample, if I asked you now to calculate the median and we ignored that 49, which is what we should do because it is an outlier, a number that appears outside the range for our checking for outliers formula, I would actually only use the values from 21 to 33. And this is why when people are doing statistics, they will first check their numbers, especially when those numbers seem far removed from the rest of the sample, whether that number should be included or it should be discarded. They will then base their sample information, things like their median, their mean, their interquartile range, based on whether they have discarded those values for the outliers or not. Let's go and look at one further example, and this one is going to be based on our chart that we used earlier. It says, using the given BMI chart, answer the following questions. What is the median BMI for a child aged 11? Well, let's go back to our chart that we had earlier, the body mass index chart. We're going to have to locate the child's age, which we said was 11. Let's just do that again. There it is. And we want to know the median BMI. That means we've got to look at the line that is at the 50th percentile. And usually that one is slightly darker, as is the case in this example. That means we're interested in this point. The BMI over here reads at 15. So to answer the question, BMI equals 15. And we can put in the units, which are kilograms per meter squared. Question number 2 says, or B, above what BMI would be considered obese for a 12-year-old child? Again, going back to our chart, 12-year-old child would be obese when they are above the 95th percentile. So any value above that for BMI. And that's the value 24,5 kilograms per meter squared. Sorry, 24,5. Let's just erase that. (24,5) kilogram per meter squared. Question C says, what BMI range is considered normal for a 6-year-old? Remember, the word is asking range here. That means we're going to have to give two values. Again, going back to our chart, we're now looking at a 6-year-old. That's over here. The range of normality will fall in this case between the 5th and the 95th percentile. So in other words, I'm interested in this value here and this value here. The BMI here is, let's make it 14, and let's see over here, it is about 18. So the range of values that would be considered normal for a 6-year-old is a BMI of 14 to 18 kilograms per meter squared. Question D says, would a 14-year-old with a BMI of 15 be considered to fall within the normal range? Well, let's go and see what a 14-year-old with a BMI of 15, where does he fall? 14 years of age, he's got a BMI of 15, that's here. So for the 14-year-old, that's this point over here. Notice that falls below the 5th percentile. That means we can say with certainty that this child would not fall within the normal range. So the answer here would be no. What we could say is that this child is actually underweight for his age, because he is falling below that 5% or 5 percentile range. And then we have a last question here. What percentage of 12-year-olds would have a BMI of 22? That should actually read or less. So let's fill that in here. So a BMI of 22 or less, looking at our chart, and we said this is for 12-year-olds, so we're looking over here. The 22 percentile, or the 22 BMI, falls over here. So that value is round about there. And if you look, it's just under the 90th percent. So we can say with certainty that 90% of 12-year-olds have a BMI of 22 or less. We could say that another way, that only 10% of 12-year-olds have a BMI that is above 22. To recap today, we've covered a number of ways to represent data. Those ways included a frequency table and a cumulative frequency chart. We also had a look at stem and leaf plots, as well as a box and whisker diagram. And then we turned our cumulative frequency chart into a diagram known as an ogive. We used this ogive to chart information regarding percentages. Of course, our BMI chart that we've just used in this final example is a very good example of how ogives get used to answer certain questions regarding statistical information. I hope you've enjoyed today's presentation.